I bring that to the table and I tell you there is no evidence whatsoever that this is a bioweapon or that it was accidentally released from the Wuhan lab. Today, with the genetics we have on these viruses and how we can do testing, we can almost date them, almost like carbon testing. So radiocarbon, you want to know how old a block is or something like that. This thing clearly jumped from an animal species probably the third week of November to humans. And pangolins, these scaly anteater-like animals, are a very good source because we have coronaviruses just like those in these animals. And it got into a human. So, we've surely had a lot of challenges with that, but I don't believe that there's any evidence linking this to, an intentional release or an accidental release, or that it's an engineered bug. It's not.
My friend Duncan and I did a show back in 2012-ish, somewhere around there, with Sci-Fi, where we went to the CDC in Galveston, and we talked to them about that very thing. And they said the real concern is just actual diseases. It's not man-made diseases. It's just naturally occurring diseases.
That's exactly it. I mean, look at where, we could not have crafted a virus like this to do what it's doing. I mean, we don't have the creative imagination or the skill set of some.
My name is Federico Katzen. I'm a senior staff scientist here at Life Technologies in the synthetic biology business segment. The invention came from the customer insights. They told us what they needed. They needed a cloning system that is sequence independent. In other words, a system that shouldn't rely on sites in the sequence, like restriction sites. At the same time, they needed a system that doesn't leave scars on the final construct, like, for example, restriction sites as well. And finally, they needed, at the same time, a system that can assemble a variety of fragments, not just one at a time, but multiple fragments at a time. So what we realized after a few iterations is that, experimental iteration, is that the homologous recombination would be the solution. So what we've done is to implement two types of solutions, one in vivo and one in vitro. The one in vitro is the GeneArt seamless assembly kit, and the one in vivo is the GeneArt high-order genetic assembly kit. So the GeneArt assembly portfolio is actually composed of three major products. First, the GeneArt seamless assembly kit, which is a kit for assembly up to 4 fragments, DNA fragments, in a seamless way, relying on homologous recombination, but it works with a purified enzyme mix, so the assembly is done in vitro. The second kit is the GeneArt high-order genetic assembly, which also relies on homologous recombination, but the whole assembly is done within the cells. It's done by yeast. So a few advantages come with this kit, which is, first of all, the dynamic range is much wider. It can go from a few bases, assembly of a few base pairs, up to 100 of kilobases. As well, this kit can assemble fragments that do not share homology between them. The homology can be provided in trans by linking or stitching oligonucleotides that can be ordered separated. The final product is a site-directed mutagenesis kit that relies on the in vitro homologous recombination properties of the first kit, which is an enzyme that actually grabs the end of PCR fragments and stitch them together. As I mentioned before, we have 3 products as part of the portfolio. The first one is the GeneArt high-order genetic assembly kit. As far as I understand, there is no other similar product in the market, so we are unique in that respect. As far as the second product goes, the GNARD seamless assembly kit, there are other similar products in the market. However, we have some enhanced benefit with respect to cloning efficiency and simplicity. Third product, the mutagenesis kit, there are other competitors in the market, but the fact that our kit relies on a recombination reaction that boosts the mutagenesis efficiency to a much higher level.